Alright, welcome to the AQA AS chemistry video. Today we're going to be doing mass spectrometry. Now, mass spectrometry is an extremely precise technique. The theory is covered mostly in the physical chemistry section. So this is the organic section. So when I get to the physical chemistry section, I'll go more into the depth of how mass spectrometry actually works. But today I'm going to be just going through how to actually read the spectra and general things like that. So let's get into it. So when we're talking about identifying the compounds, the first step is to identify the molecular ion peak, and this gives the mass to the compound. The molecular ion peak will have the highest value. So for example, if I have ethanol has a MR of 46, and we can tell that because it's molecular ion peak, the highest value is 46. We're not talking about the highest peak, we're talking about the on the x-axis, which has the highest peak, and that would be and that's 46 for, and that's allowing us to identify ethanol, which has an MR of 46. We know the compound that we have is ethanol. Generally, when we're talking about mass spectrometry, we're using this to identify a compound. As I said before, it's identifying compounds. You don't know what the compound is, we use spectrometry. This is what it's useful for. Another example, the molecular ion peak will have the highest value. So, for example, the mass of ethylene dioic acid, that's the formula for it there, has a peak of 90 milligrams per mole. The reason it's 90 milligrams per mole is because milligrams per mole is because mole is equal to mass over the MR. And if we're talking about the MR, if we want to know what the MR is, just the mass over the moles. Just a little something there. I mean, it's not really that impressive or that deep, but you know, it's there, giving you guys knowledge. So, but if you're doing the same theory again with ethylene dioic acid, its peak it has an MR of 90 milligrams per mole, and so the molecular ion peak will be at 90 if you did the same thing for ethylene dioic acid. Highest resolution mass spectrometry. So the highest resolution mass spectrometry is so sensitive that it can be used to measure single atoms, and this technique can also distinguish between molecules which have only a small difference in their molecular masses. So if we're comparing butane and propanol, right? A good example of this difference is between butane against propanol, because both butane and propanol have a molecular mass of 58 grams per mole in the periodic table of, sorry, not periodic, if you're doing the MR of butane and propanol. So if you found that the molecular ion peak was so if you found out that in the data book that they both have a molecular mass of 58 grams per mole, you might find it difficult. How would I be able to separate? How would I be able to distinguish between the two? Because if I didn't know what the compound was and I knew that it was 58, how would I be able to distinguish? But the thing you need to realize is that with this 58 here, this is for this is a very low sensitivity mass spectrometer, right? This is a low sensitivity mass spectrometer. Because if you look more accurately, the actual masses are 58.078 grams per mole for butane and 58.046 grams per mole for propanol. And this is because the relative masses of hydrogen and oxygen are very slightly different to the rough values of 1 and 16. So, you know, it's not gonna. So it's for every compound. They're all different. They're all different. They may be slightly similar if you round them to a certain number, but they're all different. So high resolution mass spectrometer can distinguish between these small differences, whereas the low resolution spectrometer can't. If the high resolution spectrometer shows a mass of 58.078 grams per mole, we know that the molecule must be butane and not propanol. And if the high resolution spectrometer shows a mass of 58.046 grams per mole, we know the molecule must be propanol and not butane, and that's it.